All right, welcome back. So we're going to continue on with some more examples in mathematical induction. Just a very quick recap. We said mathematical induction, the definition is we start with the P of n. So we start with defining what the open statement is. Remember, the open statement is a true or false statement. So it's not it's not a function, right? So it's a true or false statement. The second thing that we have to do is show its basis. So what is the smallest object in the universe and is it true? So we have to show it to be true. If we find that the basis is false, we stop and we say this statement is false. And then we go on to the induction. Is it true that every P of n implies P of n plus 1 or every P of k implies P of k plus 1? So we show those three things and then that is our whole proof. And we talked about why those three things are enough to say that the whole universe is also true. All right, so let's do a few more examples. And what you're going to see is the next few examples are very diverse. The strategy that we use is the same, but the proofs themselves are very different. And in fact, they're proving very different things. But notice that we can all use mathematical induction for this. So let's start with 7-5 here. And 7-5 is talking about that we want to show the inequality that n is less than 2 to the n for all positive integers n. Now, what you'll find is that most of the mathematical induction proofs are of this form where we say prove blah, 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 blah for all positive integers or for all non-negative integers or for all integers that are greater than whatever. So this is the form that usually a statement like this would take. So let's try to prove this. So first we start with our P of n. So here's our number one step. Okay, so our first step is our P of n is a statement that n is less than 2 to the n. Make sure once again that this is a true or false statement and not a function. Okay, and we want to prove it for all n, which is a positive integer. Now, again, I stress that in this example, it's actually pretty straightforward what our P of n is. It's not always going to be the case that it is this straightforward because sometimes we need to figure out what exactly is the statement trying to say. So we're going to see a few examples coming up. But the next example is, or sorry, the next step is that we need to do our basis. So our basis is the P of the smallest object. Now in this case, the smallest object is 1. So P of 1 is the statement 1 is less than 2 to the 1, okay, which is a true statement, right? So it's true, so we can move on. Once again, if we find that this is a false statement, we stop and we say this statement is false. All right, so number 3, we're going to say, we're going to prove P of k implies P of k plus 1. So let's assume P of k is true. Okay, so what is P of k? It says k is less than 2 to the k. You always need to write this out. I know it's kind of redundant to write it out, but uh, it is part of the proof, right? So in order to show P of k implies P of k plus 1, you must write this step down. So remember also that we need to take P of k and then move to P of k plus 1. So on the side, I'm going to figure out what P of k plus 1 is, what the statement P of k plus 1 is, and it is that k plus 1 is less than 2 to the k plus 1. All right, so given that k is less than 2 to the k, can we show that k plus 1 is less than 2 to the k plus 1? Okay, so the first thing I'm going to do is start with my premise. So if my premise is true, then so is the following. K plus 1 is less than 2 to the k plus 1. Okay, so I just added 1 to both sides, right? So I know that k is less than 2 to the k. I just add 1 to both sides. Surely this is still true. Now, are we done? Well, no, because we want to show that the k plus 1 is less than 2 to the k plus 1, right? So the plus 1 has to kind of end up in the top there. Now, I just want to, again, say that from mathematics, we can also say the following, 2 to the k plus 2 to the k. Now, in it, you might be saying, why did I write 2 to the k? In a second, you'll see exactly why. But essentially, why I can say the left-hand side is less than the right-hand side is because 1 is always less than 2 to the k. Now, again, you might be saying, why, isn't it? It's not always the case, but figure out what the universe is. The universe is positive numbers. So K are positive numbers, right? So they're not negative numbers and they're not fractional numbers, right? So in this case, we can say surely that 1 is less than 2 to the K because K is strictly greater than 0, right? So it's 1, 2, 3, or whatever. So this must be the case. So therefore, this is less than this. Okay, now what is 2 to the k plus 2 to the k? Well, this is nothing more than 2 times 2 to the k, which is 2 to the k plus 1. Okay, so you'll notice that in this example, I kind of worked from both directions, right? So I visualized that I needed to show that k plus 1 is less than 2 to the k plus 1. And then I said, what is 2 to the k plus 1? Well, it's 2 times 2 to the k, which is 2 to the k plus 2 to the k. And then I make that link between the less thans. Okay, so I hope this is useful. I hope you can see the link between the two sides. But generally, this is the process that we would go through in order to show less than. Okay, so inequalities we can also show using mathematical induction. And by the way, that's it. That's the whole proof. So given that P of k is true, we've derived the statement P of k plus 1. Right? So this, therefore, P of k plus 1 is true. Okay, so again, there's some practice questions in your textbook. I highly recommend that you go through those practice questions because they're very helpful. Being able to go through the process yourself and for different types of proofs, it's actually very helpful to understanding mathematical induction. Okay, but let's do another one that's actually quite different, but again, still using mathematical induction. So in the second example, I want to prove that n cubed minus n, this form n cubed minus n, is divisible by 3 whenever n is a positive integer. Okay, so again, we're dealing with positive integers here. So again, you can probably guess what the universe is in this case. So I'm going to prove that n cubed minus n is divisible by 3. Now, there's many ways to express divisible by 3. Okay, you may be able to think of some of them. But one of the definitions that we talked about before is this straight line, right? So when we said A divides B, then B is divisible by A, right? So B was a multiple of A. So we can use the same concept here. And if I want to show that n cubed minus n is divisible by 3, well, it's the same statement. So this is our 7-6. This is the same statement as saying 3 divides n cubed minus n. Now just take a second just to convince yourself that those two are equivalent statements. Okay, so this statement is saying 3 times an integer is n cubed minus n. Okay, and we want to prove it for all n that is in z plus. Okay, so 3 times an integer is n cubed minus n for every n in the set z, set plus. All right, second step is our basis. So what is our basis? We want to show that P of the smallest object is true. So in this case, once again, we have the smallest object as 1. So is it true that 3 divides 1 cubed minus 1? So is it true that 3 divides 0? And the answer is yes. 3 times an integer is always equal to 0, or 3 times an integer is equal to 0, which is 0, right? So in fact, you can go even further. Anything divides 0, right? Anything divides 0. Um, don't get this mixed up. We are not dividing by 0, right? We're saying 3 times an integer is equal to 0. So this is a true statement. Number 3, we assume P of k. So P of k statement is 3 divides k cubed minus k. All right, so now I'm going to take an aside here. In this case, we have to really see where we're going, right? So where we are going is we want to show P of k plus 1, which is the statement 3 divides k plus 1 cubed minus k plus 1. Now, if we do a little bit of FOIL, if we just multiply it out, we can use actually um, the binomial theorem that we talked about before. This works out to be k cubed plus 3k squared plus 3k plus 1. So that is that. And then I'm going to minus k minus 1. So minus k minus 1. So please verify my math. But a couple of things you can see from this is that we have that cancel out. So we have the plus 1 and minus 1 cancel out. And now we can also see that we have a k cubed minus k here. So k cubed minus k, that's divisible by 3, right? Because we've assumed it from p of k. So we've assumed that 3 divides k cubed minus k. We also see from the other two terms that we have 3k squared and we also have 3k. Both of those are also divisible by 3. Okay, so let me repeat that. So k cubed minus k is divisible by 3. 3k squared is divisible by 3. 3k is divisible by 3. All three of these are divisible by 3. When we add them together, it will still be divisible by 3. Okay, but how do we make this argument? Because we're kind of going backwards here. So how I'm going to argue this is that since P of K is true, okay, so because P of K is true, that 3 divides K cubed minus K, therefore, so now I'm going in the forward direction, therefore, 3 divides K cubed minus K, and then plus 3K squared plus 3K. Now, I can make a claim here, and I can just put on the side because um, uh, k is an integer, right? And 3 divides 3k squared plus 3k. Okay. Now, the rest of this is so this is divisible by 3. This is divisible by 3. I can say that 3 divides k cubed minus k plus this thing because of theorem number 1. So also, so and theorem 1 from our number theory section from number theory. Okay, so I hope you understand what I mean by that. Okay, so the first thing is that 3 divides 3k squared plus 3k because they're threes, right? They're multiples of 3. And then if I add it to something else that is divisible by 3, it is still divisible by 3 because of that first theorem from number theory. So if you don't remember that theorem, it says if A divides B and A divides C, then A divides B plus C. I can add the two things together and A still divides that. Okay, so I hope you understand that step. So the next step is quite simple. So therefore, we can also say that 3 divides k cubed minus k plus 3k squared plus 3k plus 1 minus 1. So if we add a 0, then it's really just the same number, right? So hopefully this step is intuitive. So therefore, 3 divides k plus 1 cubed plus k plus 1. Sorry, minus k plus 1. And this is our statement P of k plus 1. All right, so again, we need to make an argument going forward, right? So because P of k is true, therefore, this is true, therefore, this is true, therefore, this is true. And then eventually, we need to get to P of k plus 1. So that's always the strategy on how we do mathematical induction. Now, the next example, 7-7, I'm going to leave a little bit later. In fact, I think we're going to take a look at it in the in class. So I'm going to leave that for now. I'm going to skip over it. And instead, I'm going to tackle the number of subsets, which is 7-8. Now in 7-8, I have this I have this equation that I want to prove. I want to prove that given a set S, that the size of S, oh, sorry, let me change this for 1 second. Okay, so I wanted to add the exponent there. So if the size of S, if the size of set S is equal to n, then S has 2 to the n subsets. For all n, which is in non-negative integers. Okay, so there's a couple things that I need to talk about here. Clearly, this is my P of n for this question. So I'm just going to label that as my P of n. Now, in this question, because we want to prove the subset equation, right? So when we said there's n elements in a set S, there's going to be 2 to the n subsets. We talked about this earlier. But what is the smallest possible subset that you can have? What's the smallest possible set S that you can have? Well, the answer is empty set. So that's why we are instead doing the proof on set n here, because n starts at 0. Okay, so the smallest case that we're going to deal with here is P of 0. So our basis is going to be P of 0. What is that statement? Well, the size of S is 0 implies S has 2 to the 0 subsets. Is this a true statement? So when we have the empty set, so when size of S is 0, how many subsets does it have? Well, it has 1, which is the empty. Remember, empty set is a subset of anything. So this is a true statement. S has 1 subset. All right. So since this is true, then our next step is we're going to assume P of k is true. Okay, so assuming P of k is true. So that means if the size of S is equal to k, then S has 2 to the k subsets. Now, how do we show that, in fact, the statement P of k plus 1 is true? So now let's try to visualize what is the statement P of k plus 1. So P of k plus 1 says if S has k plus 1 elements, then it will have 2 to the k plus 1 subsets. Now, this is going to be a statement that is proven from our basis, from our assumption, P of k. So in English, what is that really saying? It's saying that from the statement P of k, if I give you one more element, okay, so now I know that k is true. If I give you one more element, then this is going to double the amount of subsets. Now, just take a second just to make sure that you understand what I said there. The statement P of k plus 1 says, if I give you one more element in the set S, this is going to give you double the amount of subsets because we want to show that it has 2 to the k plus 1 subsets. So this is going to double the amount of subsets that we have. So how can we make that argument? So let's give a very quick example on the side here. So let's say S is equal to the set 1, 2. Okay, so I have the set 1, 2. So now the size of S is 2, and so the subsets are the following. So we have the empty set, we have the set 1, we have the set 2, we have the set 1, 2. Okay, so there are 4 subsets altogether. So at this point, our equation makes sense. Okay, but what if I add one more element to this? So let's call this S prime, maybe. Okay, we'll call this S prime. And S prime is going to have the same amount of objects as an S plus an extra object. We'll call it X. Okay, so here's my argument. Every subset that I've defined for S is also a subset of S prime. Okay, say that again. All of the subsets that we have for S, these ones, 1, 2, 3, and 4, all of these subsets are also subsets of S prime. Okay, so that's the first thing. So if I want to come up with a subset for S prime, the first thing I can do is take one of the subsets for S. Okay, what is another subset of S prime? Well, it's the subset that I just took along with X. And now I can make this argument for every one of the subsets that I had in S. Okay, so I'll say that one more time. What are the subsets of S prime? They include the subsets of S, but also for every one of those subsets, I can add an X to it as well, and it's also a subset of S prime. So I hope you can see that S prime is going to have 2 times the amount of subsets as S. Okay, so here's my argument. So let S prime be equal to S along with an extra element X. Okay, so S along with an extra element X. And so the size of S prime is going to be equal to k plus 1. Okay, now for each subset, we'll call it A. for each subset A that is a subset of S, okay, so each of these four subsets that you see on the right-hand side, I'm going to define two subsets. So number one is that A itself is a subset of S prime. Okay, I hope you can see that. If it's a subset of S, surely it's a subset of S prime. Secondly, A along with this new object X is also a subset of S prime. Okay, so from this, I hope you can see that therefore the number of subsets of S prime is equal to twice the amount of the subsets of S. Now we already know that the subset of S is 2 to the k, so this is equal to 2 times 2 to the k, which is 2 to the k plus 1. Okay, so we know from the assumption that we made before, that the number of subsets of S is 2 to the k. So therefore, the total number of subsets of S prime is 2 to the k plus 1. And that's it. That's the end of the proof. This shows the statement P of k plus 1, and that shows me the end of the proof. Okay, so we've just done a lot of examples, or many examples of proofs that we can make with mathematical induction. So notice the strategy that we used, like all four of the examples that we've done so far, the strategy that we've used is exactly the same, right? So list out P of n. What is the basis? Is the induction true? And we showed all of those things. But the proofs themselves are very different. They're proving very different things. And that's what you're going to see in the textbook as well. So the textbook, when you're asked to do a mathematical induction proof, they're actually very different, right? They're very different proofs, but we use the same strategy and we're able to argue in the same way. Okay, so what I've just told you about, this is an example of what we call regular mathematical induction. Okay, so I know I really haven't used the word regular mathematical induction, but this is the most common type of mathematical induction. So to contrast this, there's another type of mathematical induction, which is called a strong mathematical induction. Okay, there's one called strong mathematical induction. So the strong form of mathematical induction is very similar. We use the same basis and we use the same induction, but the way that we show the proof is slightly different. So what I mean by this, and let's do a white slide here, a white screen, and let me show you what the difference is. So the mathematical induction proof that we saw before, which I'm going to call regular mathematical induction, is defined as following. So P of 1, so this is assuming that we have for all n in Z plus. So let's say Z plus is our universe. So we start with P of 1, and then we show that for all k, P of k implies P of k plus 1. Okay, so we're going to show this, we're going to prove this, and then we make a conclusion that for all n, P of n is true. Okay, so what about strong mathematical induction? What about the difference between regular and strong? Now, sometimes regular induction is not quote unquote strong enough. So what that means is if I assume k, if the only thing I know is k, I can't make the jump to k plus 1. Okay, so it's a proof that is difficult in that way, that if I only assume k, I can't show k plus 1. Okay, so instead of assuming k, I assume everything up to k. So what I mean by that is the strong case is I'm going to assume, or I'm going to show that p of 1, p of 2, all the way up to some p of k is true. Okay, that's part of my premise. So P of 1, P of 2, P of 3, all the way up to P of k is a true statement. And then I'm going to show that P of 1 all the way up to P of k implies P of k plus 1. So again, what I said before is if I only know P of k, that's not enough to make the jump to P of k plus 1. Okay, what I need is everything underneath that as well. So everything from the smallest object all the way up to k is needed in order to make the jump to P of k plus 1. This is called a strong argument. So both of them, you'll see, allows us to be able to conclude that for all n p of n is true. And this is called a strong mathematical induction argument. Okay, now a couple of questions might arise here. You might be saying, well, what is K? I don't know what K is because eventually I need to show that P of K is true. Now, K is going to be different for every question. So I'm going to show you a couple of examples here. Um, and you're going to be able to see, hopefully spot a strong argument and try to contrast that with a regular argument. Okay, so just for now, understand that for a strong argument, we need to assume that P of 1, P of 2, all the way up to P of K is true before we can conclude P of K plus 1 is true. Okay, it is an argument that relies on this fact. Okay, so what's an example of this? Um, so if you remember, we talked about in number theory, we talked about this thing called a product of primes. And we said at the time that any integer that is greater than or equal to 2 can be written as a product of primes. So for example, 100 can be written as 2 times 5 times 5. Other numbers can be written as themselves if they're prime. So for example, the prime factorization, the product of primes for the number 13 is just 13. Okay, so if they're prime, then it's just the number itself. But every single number has a product of primes representation. Now, the question is, how do we prove this? So here I'm going to use a strong mathematical induction argument. So the statement that I'm going to start with, our P of n, is the statement that n has a, I'm just going to call it POP, product of primes. Okay, so I'm just going to shorten this. So n has a product of primes. Okay, the second statement is now I need to show some of the values that are on the small end. So I'm going to show P of 2. Is P of 2 true? Yes, 2 does have a product of primes because 2 is a prime number, then it's just 2. Okay, now instead of stopping there, I need to make a few more statements. So P of 3, okay, is true as well because 3 has a product of primes. It is just 3. What about 4? 4 has a product of primes. It's 2 times 2. Okay, what about 5? 5 is just 5. Let me do one more. What about 6? 6 is 2 times 3. So at least up to this point, I can make an argument that this is true, right? That this is the true statement. But how do I show that given that I can get to some point k, that I can also get to k plus 1? Okay, this is the main point of this proof. Okay, so here's my argument. Number 3, I'm going to assume that p of k is true for all, well, let's use a different variable here actually. Let's say p of I is true for all I that is from 2 up to k. Okay, I'm going to assume that p of I is true for every I that is from 2 up to k. So what does that mean? That means 2 has a product of primes, 3 has a product of primes, 4, 5, 6, all the way up to k. They all have a product of primes. This is my assumption. Now, right away, I hope you can see how this differs from the assumptions that we made before. The ones we made before is just p of k is true. That's it, right? But now we're saying everything is true up to k. All right. So so there's a couple of things that we can argue here. So if p of k plus 1 is prime, okay, then I can say p of k plus 1 is true right away. If p of k plus 1 is already prime, then by definition, the product of primes is just itself. So that's clear that, there's not much argument to be made there. P of k plus 1 must be true if it's a prime number. But what if it's not a prime number? So on the other hand, if p of k plus 1 is composite, then what can we say about p of k plus 1? Well, if you remember back in number theory, we said if a number is composite, it can be written as a times b, where a and b is somewhere between 2 k, and a and b are integers, or at least in this case, positive integers. Okay, so that is the definition of a composite number, because two integers multiply to k plus 1 other than 1 and itself, right? Other than 1 and itself. So it's got to be somewhere between 2 and k. Okay, but what did we just say about every single number between 2 and k? Look back at the assumption. We said p of I is true for every I between 2 and k. So that means in particular, a and b have product of primes. Okay, so from the assumption, right, the assumption being this thing, from the assumption, we find that a and b have product of primes. And therefore, we can say k plus 1 has product of primes. And that's it, right? Because a and b themselves have a multiplication that multiply to, have a multiplication of prime numbers that multiply to k plus 1 to themselves. Therefore, it has a multiplication that multiplies to k plus 1. Okay. All right, so I hope that that makes sense. Now, I hope also that you can see that this is a strong argument. Okay, this is a strong argument once again, because we are assuming that every single case between the smallest and the k are all true, right? So the smallest input and also the k, everything in between is true. Now, let's analyze for 1 second. If we didn't assume this, if we didn't assume every single case between 2 and k, can we make this argument? Okay, so can we say that that both a and b have a product of primes? And the answer is no. The only thing we know, if we only assume k, is that k has a product of primes. That might be useless to us, right, in this proof. So I hope you can see the difference. We need the fact that everything has a product of primes before we can argue for k plus 1. I hope you can see what I was talking about before. Okay, so in the regular induction, k is enough to argue for k plus 1. In the strong argument, we need everything leading up to k before we can argue k plus 1. Okay, small difference, but very important to our proof. Okay, let's do one last example here for this video, and then we'll move on to our next concept. So another strong mathematical induction proof, just to make sure that we understand this concept. So here I might have to explain a little bit. When you see postage, okay, so postage means how much do you have to pay to send a letter? Okay, so I don't know how many of you are aware of how to send a letter, but I'm pretty sure there's still post offices out there. But you bring a letter in and you have to buy stamps. And when I was little, you needed to buy enough stamps to send the letter. Now, you can go over, but that's not really that, that's not smart, right? Because you're actually paying more in order to send the letter. So what you want to do is pay exactly the amount of postage that you're going to need in order to send a letter. So let's say that any postage is like a valid postage is something greater than or equal to 12 cents. But what the post office is selling is only 4 and 5 cent stamps. So the question is, can I always buy 4 or 5 cent stamps to exactly cover the postage? So the question is, for example, can I make 12 cents? Right, so can I do 12 cents given that the post office only has 4 or 5 cent stamps? And the answer is yes. I can do 3 4s, right? If I buy 3 4 cent stamps, I make 12. What about 13? Well, I can do a 4, another 4, and a 5. So 4 plus 4 plus 5 is equal to 13. Now the question is, can I do this all the time? Right? So is it true that any amount of postage can be made by only buying these types of stamps? So again, we are going to use a strong mathematical induction proof here. I'm going to start with my P of n, and this P of n is going to say n cents can be made using only 4 or 5 cent stamps. Now, this proof is going to be proven for all n, which is greater than 12. Okay, so n is z in z plus, and n is greater than or equal to 12. Okay, so this is the universe that we're working on. So the smallest value that I need to consider is 12. Okay, so number two, I'm going to start with my basis. Now, again, this is a strong mathematical induction proof, so we're going to have to go a little bit further than just the first case. But is the first case true? The answer is yes. We can do 4, 4, and 4. All right, so if I do 3 fours, that makes 12. Okay, what about 13? Can I make 13? P of 13. And yes, we can, because earlier I said we can do 4, 4, and 5. What about 14? Well, 14, I can do 5, 5, and 4. So 5 and 5 make 10, and then 4 makes 14. Let's do one more here. P of 15 can also be made by doing 5, 5, and 5. Okay, now can we go further with this? Can we go on forever like this? So here's my argument. Number three, I'm going to argue that let's assume that P of I is true for all I that is between 12 and k. So let's say we can get up to some point k. Now, we've shown that we can get up to 15 at the very least, but let's say we can get up to k. Can we show that k plus 1 cents can also be made using only 4 or 5 cent stamps? So right now what we know is 12 all the way up to k can be made, but what about k plus 1? Okay, so my argument is this. K plus 1 cents can be made by. All right, so let's think about it. How do we make 16 cents? Well, for 16 cents, I'm going to need 4, 4, 4, and 4. Basically, 4 4-cent stamps. So would you agree to make 16, it's the same method as making 12 and then adding another 4-cent stamp? Okay, so in order to make 16 cents, I'm going to look back at how I made 12 cents and then add a 4-cent stamp to it, and then I'm going to get 16. How do I make 17? I look back at how I made 13 and then add another 4-cent stamp, and I'm going to get 17. Okay, so can we generalize this? So n plus 1 cents can be made by using the method for k minus 3. Now, just notice that the difference between these two cents is 4. Okay, so again, if k is 15, right? So imagine k is 15 here. How do I make 16 cents? I look back at 15 minus 3, which is 12, and then add another 4-cent stamp. That's it. That's my argument. Now, I hope you understand the argument that I made here, but let's see how this is a strong mathematical induction problem. So again, if I don't assume that I know everything from 12 all the way up to k, can I make this argument? The answer is no. If the only thing I know is k, well, what is k minus 3 cents? I don't know. I don't know about that. So that's why I needed to assume everything up to k. So anytime we need to do that, this is going to be a strong mathematical induction argument. All right. So um, all right. So the last thing I want to mention about this problem is how many bases, how many basis steps do I need to do? Because here I did I did 4, right? I did 12, 13, 14, and 15. But in the previous example, I didn't do that much. So the question is, the answer to that is it depends on the question. So in this case, if I only show you 12, 13, and 14, let's say I left out 15. Okay, if I left out 15, would I be able to make this same argument? So let's say 15 wasn't there, okay, and we only got up to 14. Then we would ask, well, how do I make 15 cents? I make 15 cents by looking at how I did 11 cents and adding another 4-cent stamp. Well, notice we don't know how to make 11 cents, right? So in order for our argument to work, in this case, I at least needed 4 cases. I need 4 cases in the basis. I hope you understand what I mean by this, right? So there is actually another argument here that involves 5 cents. So if I say P of 12, P of 13, all the way up P of 16 is true. So if I do all of that, and then I can argue that I can look back 5 spaces and then add another 5 cent stamp, right? So I can say, how do I make 17? I look back at how I made 12, and then I add a 5 cent stamp to that. So there's a similar argument here. So this is not the only way that I can prove this. I can prove it along the lines of the 5 cent stamp as well. But either way, we need enough in the basis for me to make that jump. Okay, so that is one of the characteristics of the strong mathematical induction. Okay, so I think we have enough. So there's going to be a lot of practice in the problem sets in the in-class as well as in the textbook. So do have some practice with mathematical induction. It is actually a pretty important topic. That's why we spent so much time on this. So we will go forward and we'll talk about some other concepts, but we're going to have a few more mathematical induction proofs in the next video. So look for that. But for now, I'm going to put a stop to this video and I will see you next time.